1949 by Ehrenberg and Side, but no one noticed it so much before Bom and Aronoff again rediscovered it in 1959, so 10 years later. Then Chambers confirmed it experimentally in 1960, but people were still not convinced, and it took up to 1986 when another person called Tonomura, he did a different experiment which you could not argue with, and the Bom Arnold effect was confirmed to be true. Okay, this was in 1986. Now going back to 1964, this was when the quantum computation, which is really in fashion right now, that took off. So all this while, there was one group led by Einstein and others who believed in the quantization of energy and momentum and all this, but they did not believe in the probabilistic picture of the electrons and the wave functions. So this was because they felt that somehow quantum theory was incomplete. And the fact that we were not able to deterministically obtain results was the result of not knowing some extra variables that were definitely present. So Einstein, Podolsky, and Rosen, these are the three people who proposed the famous Epr paradox. They claimed that there must be some hidden variables which were properties of the system, which would tell us exactly what state the system was in. So it would not, it was just because we did not know it that it seemed that the quantum system was probabilistic. But in 1964, Bell did a mathematical analysis, and he showed that such hidden variables are not possible. And if you had local hidden variables, then the phenomena that quantum theory was able to explain could not be explained anymore. And if you assumed that the hidden variables had to explain these phenomena, then these hidden variables became global and not local. So they were no longer properties of individual particles in the quantum system, but of the whole system, which meant that then the hidden variable theory would also not be deterministic, and this strange correlation between different parts of quantum systems, even if they are separated by large distances, this would continue to be there. So the hidden variable theory would not convert the quantum theory into a deterministic theory. It would remain a probabilistic theory. And from this point, people started investigating this so-called quantum entanglement in a mathematical fashion. Okay, and then this led to all kinds of quantum theories focused on using this entanglement as a way of storing information, so as memory as well as for computing things. And this was an entirely different sort of development because you had to have different algorithms, you had to have different devices, different logics, everything had to be redone. So it took a long time from the 1960s till today. So the first quantum computers have just come into production. And I will list some of the main developments in that direction because I think this field will really flourish later. So maybe you get interested in this and study a little bit more. In fact, one person from Kolkata itself, Professor Chakraborty from SINB, Taha Institute, he was one of the first to theoretically show how you can have a quantum algorithm which was superior to a classical algorithm, so for optimization. So this is called annealing. You don't need to pay so much attention to what it exactly is because these things are very complicated and mathematical, and I myself don't understand it completely. But the thing is, so he showed theoretically that this as optimization moving forward. Yeah, anyone questions?
Ma'am, can you please explain how Epr paradox was explained?
Okay, so this will take some time. So Epr paradox, it was explained, or rather it was shown that it was not a paradox really, in the sense that if you have quantum entanglement, so the EPR paradox wanted to show that quantum entanglement was not possible.
Yes.
Okay, but yeah, but Bell's theorem proved that anything you did, like even if you assumed that there were some properties of particles which allowed the system to know exactly what state it was in, like itself, without interference from other parts of the system, it still it would then not be able to explain quantum phenomena at all. So if you assume that there were local variables, you couldn't explain the quantum phenomena. And if you wanted to explain the quantum phenomena, these variables would become global, which would mean that quantum entanglement exists. So this is Bell's theorem. He couched it in a very mathematical terms. So, so this is something you will have to work through if you want to see.
Ma'am, I read somewhere that Bell has proved that instead of the paradox getting from the relativity, the quantum entanglement exists. But how can it explain how EPR paradox is not valid?
Um, so Bell basically proposed some inequalities which need to hold in order to
Yes.
yeah. So he showed that these need to exist for the EPR paradox to be valid. But what was shown later was that these inequalities are violated by experiments. So that was
EPR paradox has just EPR paradox just typically said that the quantum entanglement cannot be happened because if we take a great distance between two entangled particle, then for entanglement the information flow should be the greater than speed of light. That cannot be happened. How Bell solve this problem?
no. So Bell stopped, as you have said. Bell stopped there. Okay.
So is it still remains a problem, or it is explained how the information flow can be greater than the speed of light?
So it is not really explained, in the sense the mechanism for this information transfer is not understood, but the fact that it happens has been demonstrated.
Okay. So explanation is left for the future.
Yes, people still work on it. So quantum electrodynamics is one way of where people explain it, but there are still lots of problems in QED. So there, information does not travel faster than light. It travels, so that limit is still there in QED, but it still, the mechanism is still not clear.
Okay.
Okay. Yeah.
Ma'am?
Yeah.
Ma'am, you talked about some variables changing from local to global. What variables were you talking about?
So no one really knows. So Einstein suggested that there must be some such variables which we don't know, which would help us explain what state a particle was in without knowing the state of the full system. When you are breaking a system into two pieces, for example. So these are not known. These were just proposed, but then it was found that it is not. Most probably, there are no such variables. Okay.
Wait. So there are no such variables like that. Has it been proved or not proved?
This has not been proved to be not true. This was a proposition that there could be such variables, but no such variables have been found. And And Bell was one of the persons who showed that even if you found these variables, they would not be local, as Einstein wanted them to be. They would be global, even if you found such variables. But they have not been found. So as of now, we assume that there are no additional variables.
And what is the definition of particle?
Well, very simply, particles are things which have mass. But if you combine relativity and quantum, then you cannot really talk about it like that. So,
Just like we consider an electron a particle, okay? In kinetic theory, we consider gas molecules as particles.
yes, you can say. So on a simple level, a particle are things which have mass, and waves are things which do not. But with quantum theory and relativity, when you put it together, the more fundamental quantity becomes momentum. So everything possesses momentum. In some cases, so what we call particles, the momentum comes from mass and velocity, and for waves, it comes from wavelengths. So that's how I think about it. It's not a clean definition.
Also, ma'am, we know that photon has light, photon or light has wave nature and particle nature. Both nature are shown by photons. Okay, and
Yes.
then we say that a photon has traveled from point A to point B. Let's say we have a very large distance that we can observe that it has left point A and reached the point B after some time. Then
Yes.
what happens to the wave? Like wave travels from one point to other, and what is it?
Waves also travel from one point to the other.
So it is a disturbance in that region, like it slowly rises and slowly dies.
Yes. So it will be so when you say a photon travels, it's like a pulse of light. So you can think of a photon as a wave packet. So instead of thinking of it as a particle, you think of it as a wave packet. How I understand it is basically everything is a wave packet. Okay, but when the dimension of the wave packet is larger than the dimension of the body, then the wave nature manifests itself. When the size of the wave packet is very small compared to the size of the object, then it behaves like a particle and the wave nature does not show up. So even a ball that travels is a wave packet, but the wave packet is so small it fits inside the ball. So what you see is as if it's an object and not a wave. So that's how I like to think about it.
So electron is
Waves, right? So matter waves are also.
So when we consider electron as a wave, we also say that it is a disturbance in that region, electron.
Yes. So I think, yeah. So basically, we talk about particles and waves distinctly because that's how we have built up our classical mechanics. But after you learn quantum mechanics, then maybe just thinking of everything as wave packets makes more sense. Okay. Any more questions? Or can I continue? Okay, I will.
Ma'am, am I audible?
Yes, you are.
Okay, so I would like to ask that what is quantum entanglement? Like, I don't really have a fair idea about it.
Okay, so quantum entanglement is so like the example I was giving you. So you generate say two particles whose total spin is zero. Say two electrons whose total spin is zero. Okay, I only know that the total spin is zero. I don't know which is plus half, which is minus half. And then without knowing this, I separate these two electrons by a very, very large distance. Then I measure one of these electrons and I find that it is plus half. Okay, and because quantum systems collapse into eigenstates, that half will then become the plus half eigenstate of the electron, which means that automatically the other half should also collapse into minus half, because you cannot violate the total spin, right? But how did the other electron know that I have measured the first one? This is a very, so this is quantum entanglement, but it does know. So it has been shown that if you measure one electron and you find it plus half, the other one will also automatically collapse to minus half if the total spin was 0 in the first place. So, and this is called quantum entanglement. That there is this instantaneous communication between two halves of a quantum system.
Okay, ma'am. Thank you.
So, okay, and then this quantum entanglement became very important from the point of view of quantum computation. And in the 70s, you have these memory devices based on quantum, how to make these memory devices out of quantum systems. All the theory was developed. Then the model of the computer was developed. Okay. And then algorithms were developed to use these quantum systems. And finally, in 2004, the University of Innsbruck, they carried out a teleportation between a pair of trapped calcium ions. So there were two calcium ions, and they managed to transfer information from one calcium ion to the other through quantum entanglement. So they cut and pasted the quantum state of one calcium ion onto another. And now this has been done for many, many things, with photons, with electrons, and lots of things. Then the memory kept on increasing, the quantum memory that you could achieve. You have the quantum byte, the qubit. Then you have the programmable quantum computer in 2009. And now, in the last few years, we have different companies coming into the game, and they have developed quantum computers with quite a significant number of qubits, and you can actually do a calculation on it. For example, the IBM machine is freely available to anyone who wants to use it. You have to learn this quantum programming language called Qiskit, but it's quite simple to learn. You just need a few tutorials, and then you can actually do a calculation on a quantum computer. So this is a very exciting development now, and I don't know how soon you will have these quantum computers in your homes, but important quantum chemistry calculations are already being attempted on these computers because they are best suited to this. And in 2019, I think it is sort of the final acceptance of quantum physics by the physics community when the kilogram itself was redefined with using quantum concepts. So in terms of the Planck's constant, it's no longer a metal block in Paris. It is now entirely theoretical. Okay, and in 2019, a photo was taken of an entangled system, and if you Google it, you can even see this photo. Okay, so that's till last year, and if you keep up with the news, you will find that the quantum news keeps on increasing. So that was the story of quantum physics and chemistry till now, and we will go into more conventional studying. And in 120 days, you are expected to know 120 years of development. Now that is very, very difficult. So in the first course, of course, we stop somewhere in the 1930s. And in later courses, you will study various aspects. But of course, you will not come up to 2019 unless you take it up as your research topic. Okay. And like you are now being confused by quantum mechanics, everyone is. And don't feel bad if you don't understand it completely, because it is sort of beyond our senses, so no one really understands everything that happens. But it is the latest thing that is happening, and you can do a lot even without, if you know what the rules are. You just need to know the rules to make it work for you. So the first thing that we start with, according to your syllabus, is the failures of classical mechanics, and the first thing is the black body radiation. I think all of you have studied it at least in a preliminary level in school, but we will try to look at the details of the derivation, which I think is not done in school. So I will do the derivation today. Okay. So the thing was that the Kirchhoff in 1860, he measured the black body radiation, and it looked the black body radiation curves, the intensity versus frequency, and it looked like this curve that is marked quantum. So this is also the experimental curve. But when Rayleigh and Jeans applied classical electromagnetic theory to explain this curve, they got this classical curve, which just increases to infinity. So at low frequencies, they match quite well. But then very soon, it just blows up.
Ma'am, your voice is breaking.
Oh, sorry. Is this better?
Yes. Much better.
Okay. Yeah, I just moved a bit further away from the computer. Okay, so the classical explanation, it ended in what is called the ultraviolet catastrophe, because this meant that whenever you switched on the oven, for example, or you heated something, you would be blasted with UV radiation, because the intensity of the UV is so much higher than the rest. But this was obviously not true, and people were stumped on how to explain it. So there is this very nice YouTube video you can watch. You can watch it later, and there is some details are present in this link. But for now, I will just show you the derivation. So there are two things that we need to be able to explain with our theory. One is the nature of the curve itself, the fact that it goes through a maximum and the two ends move to zero intensity, and the fact that the maxima of the curves for various temperatures, they follow a relation like this, that the lambda peak into temperature is a constant. This is what is called Wien's law. So these two things need to be explained by whatever theory we propose. Okay. And what we need to compute.
Ma'am, the Wien's law is experimental or?
It is experimental. So Wien proposed this law experimentally. And then, so there is, so what we need to compute basically with our theory is the spectral energy density. Okay, and show that it is proportional to nu square. So this is. So if it is proportional to nu square, then you get this classical curve. And when you have a structure like this, which is the Planck's law, it fits the curve well. But let us see how we get this, okay? So I will now shift to my derivation. So I hope you can see this derivation. I did not want to write on the iPad today because it's a lot of steps. So what we want to compute first is the average energy per mode when you assume a continuous energy distribution. So if you have a continuous energy distribution from 0 to infinity, and the probability of having each energy is PE, which is the Boltzmann probability distribution over here, then we want to show that this average energy when we compute it is KT. Okay, so I just substitute the Boltzmann probability distribution into this expression for average energy, and then I do the integration. So what I have done is I've taken E to be x and small a is 1 by kt, and I integrate, and I get this form where z is ax, and then I integrate by parts. when I integrate by parts, I get this expression. And on putting the limits, I get kT squared for the numerator. And similarly, for the denominator, I get kT. So the average energy per mode of oscillation of the atoms is kT, classically. Then what Planck proposed was that this average energy is not a constant. He wanted it not to be a constant. So what he wanted was that the probability of having high energy modes of oscillation, these would be less. So what he said was that instead of allowing all possible energy levels, I only allow energy levels which are multiples of h nu, nu being some fundamental frequency. Okay, so then each of my energy levels,
Ma'am,
yeah.
from the classical derivation, we got that the average classical energy will be is equals to kT. So, how does this explain the classical curve? From this result, how can we come to the classical curve?
We will get there. We have not got there yet. So now we are just looking at the average energy per mode of oscillation. So, so this is for every. So in the black body, you have oscillators which are oscillating with different energies, and they are emitting radiation of equal to that energy. So when you assume that they can have a continuous distribution of energy, you get that the average energy is kT. Okay, but you have to multiply this with the number of modes. We have not done that yet.
Okay.
But the number of modes of oscillation is the same for both classical and quantum. We will come to that. Just hold on.
Excuse me, ma'am.
Then we have, yeah.
Ma'am, what does
No, I was just saying, ma'am, what do you mean by mode when you were saying above, like, you mean degrees of freedom or something like that when you are saying mode there?
Well, I mean, yes, degree of freedom, and also so like you have and then the harmonics for oscillators, all of those. Each of them are a mode of oscillation. So the fundamental and then the higher and the higher. So, so if you think of the standing waves, then you can have, have a standing wave on a string. You could have the length of the box being 1, or you can have it full wavelength, or like 3/2 times the wavelength. So each of this is a mode of oscillation. Okay, and classically, each of them have an energy of kT for oscillators. So this comes from the Equi-Partition Theorem, which says that every degree of freedom has half kT. And for oscillators, you have two types of energy, the potential and the kinetic. So each of them have half kT, and each mode has kT. So this corresponds to the same concept, that every mode of oscillation for a classical oscillator has kT energy. Okay. Fine. So, okay, so would you like me to go back to these oscillators if that is not clear? So you look at this PDF, I will show you a figure here. So if you have like a one-dimensional box here, if you see, then if the box is of length A, then when lambda by 2 is equal to A, that is one mode, that is the most fundamental mode of oscillation. And then you have this second one, where it is lambda, and then there is 3 lambda by 2. So here you can see 3 modes of oscillation. Okay. And for every mode, classically, you have an energy of kT. Now, so the average energy per mode. So I'm sorry, I will take back my words. It's not every. I cannot say that this is KT, this is KT, this is KT. But the average energy for each mode is KT. Okay. Now, now we go to what Planck did. Planck said that instead of allowing a continuous energy distribution, like here we have used an integration over all energies from 0 to infinity. Okay. Instead of that, now we replace it with a summation from 0 to infinity, where j equal to 0 to infinity. I have missed j. Okay. And you have different modes, each of which are separated by h nu. And we again use the Boltzmann distribution. And we replace h nu by kt with e to the power minus h nu by kt with x. So this quantity becomes x to the power j. And the denominator becomes this series, which sums to 1 by 1 minus x. Similarly, when I sum the numerator, I get h nu x 1 by 1 minus x squared. So this is a series sum. I hope you don't have a problem with it. And then I calculate the average energy per quantum, and this gives me the Planck's law. So this is not entirely Planck's law. This is only the average energy per quantum. But you can see that this is not a constant anymore. It depends on the frequency. Depends or on h nu, which is the energy of the mode. Then now like the question that came before, we now need to calculate the total energy. So now we need the number of modes per unit volume now. So how to calculate that? So this is the same for both quantum and classical. So we'll do that only once. So I want to calculate the number of modes per unit volume between nu and nu plus dv. So how to do that? So let's consider one dimension. So why are we considering only standing waves? That is because if the waves did not have nodes at the walls of the black body, then they would dissipate out, because there would be loss of energy every time the wave got reflected from the surfaces. And once it equilibrated, these waves would be gone, and you would only have the standing waves in thermal equilibrium inside the black body. Okay.
No, can you repeat again?
Yeah.
Can you repeat again? I will.
So the thing is that what we want is that the radiation that is emitting from a black body is in thermal equilibrium with the black body. Okay, and to do this, you allow the radiation inside a cavity to reflect off the surfaces multiple times. And in doing so, what happens is that those waves which do not have nodes or zero amplitude at the walls, they would lose energy every time they reflected, and they would get dissipated. And the only waves which would survive inside are the standing waves. So this tells us, gives us a relation between the length of this black body, the dimensions of the black body, and the wavelength of the radiation inside it. Because you can only have standing waves. Okay. So we assume a cubic cavity to simplify our derivation, A by A by A, and then so the wavelengths in every direction. So waves which are moving parallel to the x-axis, I'm denoting by lambda x, and similarly lambda y and lambda z. And you have the length having to be the integral multiple of lambda by 2. Okay. But suppose now that this wave, that one of the waves is not traveling parallel to any of the sides, then we have to do a little more calculation, but simple enough. So if you have a xy plane, then and the angle of this wave is alpha with x and beta with y. Then the wave normal and these are the dashed lines are the wave fronts. And there is a 90-degree angle between the wave normal and the wave front. So by trigonometry, you can see that lambda x, which is the x component, cos alpha is lambda. So I have drawn the wave fronts at gaps of lambda. And from that trigonometry, you can see that the relation is that lambda x cos alpha is lambda, lambda y cos beta is lambda. And we can combine them into this equality by using the standing wave condition here. So nx lambda x by 2. So I have written lambda x as lambda by cos alpha. And so given the wavelength of the radiation and the angle that it makes, I find an expression for the allowed integers. So which values of nx, ny, and nz are possible? Now if I square and add these three equations, I get this identity on the right, which is 1. Okay. So cos square alpha plus cos square beta plus cos square gamma is 1. I will provide this in the notes, but I think you are aware of this identity. And now we want to count all the possibilities for these tuples of nx, ny, nz. So what are the values of nx, ny, and nz that are allowed in combination? So to do this, we adopt a trick. So we consider a lattice of positive integers, nx, ny, and nz. So they follow 3 axes, and we take only the positive axis. So this is 1/8 of a sphere. So these points will be, this will be a spherical lattice with only positive values. And each point will correspond to a combination of nx, ny, and nz. And for simplicity, we will assume that these lattice points are unit distance apart. So unit volume of this lattice contains 1 point.
Ma'am?
So to compute the volume of this lattice, I will find the possible. Yes.
Ma'am, how the sphere will be divided by 1/8?
Okay, so if you consider a sphere in 3 dimensions and you only take the positive x, y, and z axis, then that is 1/8 of the sphere.
I'm able to understand
So if you,
how it will be.
how it will be. So you have to just imagine this in 3 dimensions. And you have a sphere with the center at the origin. Then the positive x, y, and z, they take. Okay, so let's see. So let's drop half of the sphere, which is all the negative z values. Okay. Then from the top half, you drop all the negative y values. Now you have 1/4 left. Now from 1/4, you drop all the negative x values. Then you are left with 1/8 of the sphere with positive x, y, and z.
Okay, ma'am, I understand.
Yeah.
I understand.
Okay. So then this is, so we have to basically find a volume. So we want to find out the volume of this lattice between frequencies nu and nu plus d nu. Okay. So now I say that position vector rho is considered which takes me to one of the spherical shells in this spherical octet, and you and you go from rho to rho plus d rho, and I calculate the volume of this shell. So to do this, I note that rho square is nx square plus ny square plus nz square. Okay, and this I know is given by this expression. Nx square plus ny square plus nz square is 2a nu by c whole square. From this, I can obtain an expression for nu as this. Okay. And this is rho square to the power half, which is rho. So I have nu is equal to c rho by 2a. And then I count the number of modes from nu to nu plus d nu and call this n nu d nu. So n nu d nu is the number of nx, ny, nz tuples in 1/8 of the spherical shell between rho and rho plus d rho. And then and the surface area of the sphere of radius rho is 4 pi rho square, and you multiply that by d rho to get the volume of the spherical shell. And because it is 1/8, so you divide by 8. And since every radiation has two possible polarizations, so every mode is actually two possibilities. So a wave in the z direction can have an electric field in either the x direction or the y. So you need another factor of 2 for this. So 2 waves per mode, and you get this expression, which you simplify, and you get this, which shows that the number of modes between nu and nu plus d nu is pi 2a by c whole cubed nu square d nu. Okay. And I expand it further, and this is what I get. So this is the number of modes per unit volume. What I have done, so difference between n and n bar is I have divided by the volume of the box, a cube. Okay. And n bar is then 8 pi nu square by c cube. This is the same for both the quantum as well as the classical. And then for Rayleigh genes, you multiply these number of modes with kT, which is the energy per mode, and you get the energy for radiation in the frequency nu to nu plus d. This is called the spectral energy density. And when you multiply it with the Planck's expression for energy per mode, you have this. Okay, this is again the spectral energy between nu and nu plus d. And when you plot them, you will easily see that the Rayleigh genes law is the classical one, which blows up with increase in nu. So when nu increases, nu increases, which is not acceptable. And in Planck's law, there are multiple balancing acts by the nus. So when you have in the low frequency regime, when kT is very much less than larger than h nu, then h nu by kT is very much less than 1. So you can expand e to the power h nu by kT in the series and drop the higher orders, and this gives you the denominator as h nu by kT, and you recover Rayleigh genes law. Okay. And then, but when you have the high frequency regime, then of course this dominates and damps down the spectral energy density, and the ultraviolet catastrophe is not seen. And then you can also derive Wien's law from Planck's law. So in order to do that, what you have to do is move from frequency to wavelength first. Okay. So that is simple enough. I just replace the expression nu by c by lambda, and I get this. I ignore the negative sign because spectral energy densities cannot be negative. And then I do a maxima calculation. I take a first derivative, set it to 0, and I find that. And then you do quite a bit of algebra. Perhaps you can do it as a homework. You just work it out. Okay. And then you can obtain a theoretical derivation of Wien's law as a constant. And yeah, and I will skip this for now. I will help, but I will provide this note so you can look at it later. And the other law, which you have probably studied before, is Stefan Boltzmann law. It says that the total radiation density from any heated object is proportional to T to the power 4. This can also be derived from Planck's law. And the Stefan Boltzmann constant sigma, which is the proportionality constant for this law, this was also originally obtained experimentally, but from Planck's law you can obtain it theoretically, and it agrees quite well. So these two last things I will probably ask you to do in an assignment, and then we can work this out again in class when we have time. Okay, I will stop here today. I will just go back to the presentation and recap what you need to know about black body radiation. So you basically need to be able to derive the spectral energy density, both classically and also for quantum, with the quantum assumption. Then for this, the number of modes calculation is the same, but the average energy per mode has to be computed differently. Okay. Then you need to be able to reproduce Rayleigh-Jean's law from Planck's law, reproduce Wien's law from Planck's law, and also reproduce Stefan Boltzmann law from Planck's law. Okay, so this is what you need to basically know from the point of view of your course. But it's a very interesting topic, so I would like you to at least watch the YouTube videos and the note that I linked to. Okay. So I will stop here now. Because I guess I have also provided a PDF for the black body with some notes here. So you will get some additional points over here, and the details of what I spoke about, it's written over here. So you can combine this PDF and my handwritten notes, and you should be able to do all the derivations without problem. Okay. So I'll stop presenting now. Yeah, hello. And while teaching, I'm sorry I cannot keep track of your chats, but I will answer your questions by email. Okay. And Yusuf, I'm sorry I did not find time to provide you with the details on the elliptical orbits. I will do this by this evening. Okay. Thank you all. So I close the class now.